Thank you very much. My name is Henrike Seidel. I'm a PhD student at the GU Institute for Sea Fisheries in Hamburg. And I'm not presenting on my PhD, but I have here the pleasure of presenting on behalf of my supervisor, Vanessa Stelzmüller, on a paper that we recently submitted to IC Special Issue. And it's about quantitative environmental risk assessments in the context of marine spatial management. And these are basically some early results of an ongoing project, which is called Moana. Okay. Well, I want to start with the last sentence of Heino's presentation yesterday. Accounting for the spatial dimension of ecological risk is essential to reach goals of sustainability and ecosystem conservation. And we are particularly interested in spatial patterns. And if you're not sold yet, maybe this will convince you. This is, there's a map here which nicely shows some of the overlapping activities that are going on in the North Sea. Lots of shipping routes, offshore wind park areas, conservation areas, and fishing effort. And there's also a multitude of different policies and legislations at national, but also at the EU level. For example, the Marine Strategy Framework Directive, and there's also a Marine Spatial Planning Directive underway. And for all of this, it's necessary to assess the risks of future planning decisions. And environmental risk assessments in the context of marine spatial planning have been discussed in the ICES context since 2007, roughly. But there's a feeling that there are various different approaches, and there's a need to align spatially explicit ERAs with the ongoing spatial management process. One way of looking at environmental risk assessments is here the framework of Cormier at the heart with the risk assessment. First, you start by identifying the risk. That is basically specifying the stressors and the ecosystem components that you want to analyze. During the risk analysis, you specify the probability and the magnitude of the stressor occurring, and also the impacts on the ecosystem component with a degree of uncertainty involved, which then leads to the risk evaluation. And this is basically the part where it's being decided, okay, do we need management measures, additional management measures, do we need to adapt them or not? And the paper is structured in two different parts. The first part was a literature review where we wanted to see, okay, what kind of approaches have been published so far in the context of marine spatial planning. And based on some of the identified gaps from the literature analysis, we conducted a case study in which we wanted to link the risk analysis with the risk evaluation by combining a GIS with a Bayesian network framework, basically, to showcase these steps. I was mainly involved in the literature review, and Vanessa Stelzmüller carried out the analysis. Okay, so all in all, we reviewed 32 peer-reviewed, obviously, quantitative environmental risk assessments in the context of marine spatial planning, and that was the result of a choice of predefined keywords, and that yielded a very large table, basically, where we specify scale and location and the three different steps of the risk assessment, and also present the assessment output type. Not going to go into any detail. Let me just give you a run through the basic or the main trends in terms of risk identification. Most studies looked at single or dual pressures or stresses, mostly fishing on multiple species or habitats, and only a few studies were actually looking at cumulative impacts. In terms of the risk analysis, terms of risk, vulnerability, impact were usually used synonymously. And in terms of the quantification of the sensitivity of the environmental components under study, that remained a pretty difficult task, or not pretty difficult, but basically what we found was that most of the analysis wasn't run with empirical, or wasn't based on empirical data alone. Usually it was sort of a mixed bag of model outputs with expert knowledge, and really showed that, in terms of environmental risk assessments, right now we seem not to be doing without expert knowledge, which introduces additional uncertainty to the assessment. Which also was a finding that the explicit quantitative assessment of uncertainty was repeatedly lacking in the studies. And in terms of the risk evaluation, only half of the studies actually accounted for this step, basically saying adaptation of management needed or not by the use of scenarios. Okay, so this brings me to our case study, which was conducted or spearheaded by Vanessa. We carried out this case study in the Northern Sea, in the EEZ of the German EEZ of the Northern Sea, and we have a marine spatial plan since 2008. And in this spatial plan, there are various activities which are sort of regulated or represented. We have shipping lines, forest areas for offshore wind parks, but for example, fishing is not represented, or at least not yet. And what you can see here is that these priority areas, the dark colors represent the fishing frequency of large beam trawls here as an example. They overlap for about 15% with these priority areas. So what will happen when these offshore wind parks are being developed? Well, the fishing pressure obviously has to be reallocated, has to go elsewhere, and what are the effects of that? Also, under the Marine Strategy Framework Directive, EU members are required to establish a good environmental status, and one of the environmental goals under the MSFD is to safeguard or maintain seafloor integrity. And so we came up for our case study with a hypothetical objective, which is the average relative vulnerability of benthic communities to fishing should not deteriorate with respect to current levels. And for our risk identification, we chose empirical data from PESH on 10 different benthic communities in the EEZ. And we also computed from VMS data from 2005 to 2008 for the international, actually here, this is just for the large beam trawlers, but we did this for 6 fleets, Dutch, Danish and German fleets, basically. So with this, well, you're, I'm sure, aware that risk is a product of occurrence probability and the measure of impact. And what we did, this was based on the methodology of FOC. We calculated a disturbance indicator, which describes the overall relative vulnerability of our benthic communities to bottom trawling. And this is basically defined as the ratio of the overall local mortalities and the relative recovery of our benthic community. And since we had we chose a spatial approach, our occurrence probabilities are based on the spatial distribution of our ecosystem components and our fishing pressure. Okay, so our pressures, as I said, we computed this for 6 different bottom trawling fleets. We distinguished between, beam trawls and otterboard trawls, different mesh sizes and different ship sizes, to calculate the local mortality rate for each benthic community. And this was then weighted by an impact score, IS, which reflects sort of the different fishing fleets. For the relative recovery of the benthic community, again based on the methodology by FOC, we assumed that a recovery was reached when 90% of the abundance was reached that was sort of previous to the trawling event. Now with these 2 variables, and one step back, for the impact, for our first scenario, we said, okay, in terms of the impact score of the fleet, well, all of these 6 fleet, doesn't matter how big, how small, what the mesh size is, all the impacts on the sort of benthic mortality are the same, it's all 1. Then we said, well, maybe this isn't so realistic. Let's weigh the impact of the fleets. Again, this was based on literature values. And while the large beam trawlers remained at a value of at an impact score of 1, the smaller ships were sort of devalued. And then this yielded spatial prediction maps for our local mortality rate. Here, this is an example for an equal impact score, so all ships or fleets are have the same impact, and this is the relative recovery for the benthic community. And now, and then we calculated the disturbance indicator from this. And that's basically the result. So on the left here, we have our disturbance indicator where all fleets are the same. And here we have the weighted disturbance indicator. And now, well, there are lots of values. Basically, if you remember, it's a ratio between mortality and recovery. So if you have a value of 1, then there's equal mortality and equal recovery. When you have a value above 1, you know, okay, this is a bad sign basically for your community, because indefinitely that community would become extinct. And we can see that we have quite a different distribution. Here on the left, this is much more conservative than the weighted indicator, and this is basically also due because the highest weights were given to the large beam trawl fleets, which are not fishing in the coastal areas. And this then gave the input to our risk evaluation, and we created NASA created a BN model. I know this is not very pleasant to look at, so let's not dwell on that. Not quite as fast. Basically, here we have our 6 fleets, we have our empty communities here, and this is the calculated recovery and the mortality rates. And here, this is really what interests us for now, the disturbance indicator with all fleets equal 1, and the disturbance indicator with which is weighted. Okay, and maybe you remember that I mentioned that currently 15% of the large beam trawls are fishing in offshore wind park priority areas. So we assume they're going to be built, fishing effort has to be reallocated. So what happens to our disturbance indicators? Actually, not that much. There is a slight increase, as you can see here in both, but it's, well, marginal actually, and the standard deviations are really quite high. Now, we added another 3% of total fishing frequency from the small beam trawl, which is currently fishing in these offshore wind park sites. When we add this onto the other scenario, not much happens to our disturbance indicator values. But what is really important to see here, and this is where the beauty of the the coupled approach between GIS and the BN comes in. We see a changing distribution pattern, and actually in 9% of the area we will have higher value levels of disturbance compared to former levels. And so this is really here the important bit to look at, not so much the absolute value. Okay, and this brings me to my results for the risk analysis, where we created a measure of disturbance for Bensley communities with values 1 reflecting an unbalanced state. We observed great differences in spatial patterns between weighted and unweighted disturbance indicators. And while one could say unweighted disturbance indicators are more conservative, maybe the weighted ones are more realistic, but actually both sort of represent an upper and a lower bound. In terms of the risk evaluation, as I mentioned, the absolute differences in the disturbance indicator was very small, but there was an increase of local disturbance ratios in 9% of the study areas. And so really the predicted likelihood of an area proportion is much more meaningful, as I said, as the absolute value. And this is also very important when we think of evaluating trade-offs in spatial management scenarios or management plans. If you recall our hypothetical objectives that the average relative vulnerability of friendly communities to fishing should not deteriorate with respect to current levels, well, that, under this scenario, that doesn't hold, and as a consequence would require an adaptation of current management. And this really, for us, exemplifies that spatial explicit measures are crucial, and that marine spatial planning processes should really embed an environmental risk assessment framework. Since these are early on results from the NOAA project, some of the next steps will be to include more, or to sort of represent the temporal resolution of the fleet-specific fishing pressures, and I lost the words, but more broadly, basically, also to play around with sort of the impact scenarios with the scores, the fleet scores, the inclusion of natural disturbance could also bring additional knowledge, especially in the coastal areas where species are more adapted to high disturbance, high natural disturbance. And it's also planned to expand the Bayesian net to account for multiple pressures and to expand on the benthic communities as well. Not so much focused just on infauna, but also on epifauna and benthic communities. And the last point is, well, the fishing effort now is calculated from BMS data. Once more realistic scenarios become available, for example, through individual-based models, this could really also improve the results. And with that, I thank you for your attention.